Hi, I'm Rudranil. Today we'll be doing a prediction using unsupervised machine learning, machine language, and this is basically from the given IDs dataset. Predict the optimum number of cluster and represent it visually. I'll be using R for this. Okay, first is the directory. Then we get the IDs dataset. See 150 rows, 6 variables. Let's just quickly just see through it. First column is ID, second is sepal length, sepal width, petal width, and the species. Okay, so 150 rows, 6 columns. We don't require the first column, which is the first column is ID. We don't require that right now, so we remove that. Then the summary, we got the summary for sepal length, it is 4.3 minimum, first quartile 5.1, median is 5.8, mean is 5.843, third quartile 6.4, maximum 7.9. Similarly for sepal width, petal length, petal width, and the three species are Iris sisota, Iris versicolor, Iris virginica. Now we find the structure. The structure is all numerical except the species, which are the factors of three factors. We have seen that. We import the library ggplot2, then enters the data. Now we find if there is any NA values, no, then we change. This is unique, eliminates duplicate elements. So from 150 we got to 147. That means 3 rows were unique, same in nature. We library data explorer, then we see the plot missing. Is there any plot missing? Is there? No, everything is 0 0 0 0 0. We can see, so it's good to go. The plot structure, see, it is basically nothing. This is the root has data frame 147 observation, 5 variables, and we got sepal length, sepal width, petal width, and the spaces. This is the structure. Okay, then plot histogram. We plot the histogram for all and see we got this petal length histogram, but from 2 to 2.53 it is 0. We got the petal length, we got the sepal length, we got the sepal width. It's a good histogram. Okay, fair enough. Then we do the plot density. The plot density, if you see from 2 to 3, this is 3, then 2 to 3 there is a dip in petal length. Similarly for petal width, from 5 to 0.5 to 0.75 there is a dip, and then this is good to go, and this is also is going up high and then down. Fair enough. Then we want to quickly we see the correlation. The correlation is petal width with sepal length. It's very highly correlated. Petal width with sepal width is negatively correlated. Petal width and petal length, they're very highly correlated, 0.96. So similarly you can see the correlations. Then we do a box plot. The box plot is sepal length, sepal width, petal width, with main is the name. This is the main, and then names is, this is the names you got. Okay, fair enough. This is between 4.5 to 8. The sepal length, sepal width is basically from 2 to 4, and see there are 3 to 4 outliers. The petal length varies much. It is almost from 1 to 4, yeah, or 1.5 to 4 something. Then it is less. Okay, now there are 4 outliers. Should we do anything for this exercise? I'm not dealing with outliers. Okay, now we see the ggplot, iris ggplot. I'll just show it. Yes. Okay, now see for sisota, see the sepal length is less. The versicolor, the sepal length is higher, and iris virginica, it is a little higher. So this is one, you can understand from this that okay, the sepal length of the 3 species are actually different. Similarly we do it for all. We do it for I'll just quickly I'll tell this, and rest you can do. For sepal width, see the sisota, the sepal width is high. For iris versicolor, the sepal length is less, and for virginica it is average, it is little higher than versicolor. So now from this box plots you can understand and you can see these are easy. If you just go through it, change any number, change any color, you will find what are the changes and you can understand that. Similarly, we do it for petal length. Yes, so this is again the petal length. Now this is the petal length. Fair enough. Now we change it to, yes, this is the petal length. Iris Sisota, the petal width. Now is the petal width. Petal width is low for Sisota. It is medium for versicolor, and it is high for Virginica. Okay, so we got an image of all this. Now we had four outliers. We'll just quickly we'll see, and it is of the sepal width that time. So uh, what is IQR? Just what's IQR? Its IQR is 0.5, interquartile range is 0.5. So if we see 4.05, 4.05 is the one on the higher side, and on the lower side it is 2.05. So if we quickly see, just okay, instead of going through this, I'll change it here. Summary, yes, the summary is there. Okay, now if we quickly see, uh, the sepal minimum is 2, whereas it is the outlier is, it's the first quality is 2.05. So this is one, we got a outlier, and on the higher side it is 4.05. The maximum is 4.4. so anything which is more than 4.05 is an outlier. But however, for this, as I told, we are not going to do anything. Now we will use elbow method to find the cluster. So we did set the seed at any number which you can give. This is because every time you do k means, and if you don't set seed, you will get a different result. So we set the seed at, we set the seed, if this number you can give anything, you can give 1, you can give 2, you can give 6, you can give any number. Okay, and we require the data set from 1 is to 4. 1 to 4 means we want to delete this species. So Iris data frame is 1 is to 4. Then we are doing a WCCS is a vector. We did an empty vector first. We have written WCSS, it's an empty vector, right? Now for I in 1 is to 8, that means I is going to take the value from 1 to 10. I is going to take the value from 1 to 10, this WCSS I, and within each iteration we compute within cluster close to sum of squares. We compute close to sum of squares for each number of cluster by writing sum and k means in parentheses, and k means in parentheses, right? K means in parentheses. To fit the k means to our data set x with, to fit the data set x is this one. This is given here. If you see, the k means x is there. If you see, the k means x was there. So to set that, this is the our data set with I and withinness. Now if we just hold on, I'll show you. If we write k means, if you now come down, k means, you will see this is centers. Arguments of k means are this, and I was talking of withinness. Yes, details. There is something called withinness, the vector of within cluster of sum of squares, which I was telling, one component per cluster. So withinness. So dollar withinness. Okay, so this is done. This is done. Okay. Then plot WCSS 1 is to 8. WCSS type B. Type B is both type. You can see both type. Okay. One is line and one is parallel. So it is both type. Main, cluster of clients, xlab, number of clients, ylab. This is simply, this is nothing. You main is, we are just writing the names, right? So we are going to plot this thing. Yes, see, I told you main, paste cluster of clients, WCSS, and number of clients. So only thing is this one, we are going to plot this WCS 1:8 WCSS. Now see, now where is the elbow? We are making the elbow. The elbow is at the third one. From third one, it is something similar. So this is the elbow. So we are going to have three clusters. So now K means iris data frame center 3, iteration maximum 500, in start 40. Right? K means, okay, this is the K means. X is your data, that is irisdf. Center is 3. ITR maximum is 10 lakh. We have given 500. In start is 40. Right? So this will do. Okay, then library cluster. Now we do the class plot. Class plot is irisdf. K means cluster, line 0, shade true, color true, labels true, plot chart true, span true, main is this. Now I'll again show you. So this is the thing. So now you got three clusters. This is the first cluster, this is your second cluster, and this is your third cluster. Right? We got three different clusters, and these two components explain 95.77% of the point variability. So it describes around 95.77%. Now if you change lines to 1, what will happen? The lines will go off. I'll just show you what happens. The lines goes off. Sorry, if it is 1, you see this, you get this, the centroid. This is the centroid, so you get the joining points of the centroids. Okay, so we don't need that. 0. So if you remove, sorry, which I was telling you, if you remove the shade to false, then you will not get this shades. Okay, you will not get these shades. Right? No shades are there. So I put the shade is equals to true. Okay, so similarly you can change everything and you can see what happens. Now iris data frame cluster, K means cluster. We want to see this cluster, right? So this is the cluster. The first, they have for this, all this 147, 111111, then 22, then again 3, then again 222. So they have made some clusters. Okay, we'll see these clusters. Now we want to aggregate them. Aggregate iris data frame, list the iris data frame according to the clusters and mean. Then cluster, we made the cluster profile. 3 observations, 7 variables. This is a 3 observations, 7 variables. I'll show it to you. So view cluster profile, you have that is shown it. The first cluster frequency is 48, sepal length 5.01, and sepal weight is 3.43, petal length 1.46. Anything between this range, they forms in cluster 1. Anything between this range forms cluster 2. Anything between this range forms cluster 3. So we got 3 clusters, right? Okay, now we print those clusters. The cluster 1, 2, 3, 48, 61, 38. But actually it was, we got clusters of 3 of 147. That means 49 each. But here this is 48. That means it is almost right. In second cluster there is an overlap. Yes, there is an overlap. That is here. There is an overlap. So if we can change this. ITR max and n start, if you keep on changing this, you may get a better result also. So that is it. That is how we make a cluster. That is how we make the clusters, and we can predict which one will fall into which group. I hope you have liked it. Thank you so much. Thanks. All the best.